All right, we're going to end with the last part of chapter 5 here. We're going to look at what's called the central limit theorem. And the central limit theorem, I'm going to use the example in the slides to build it out because our numbers get so big so quickly that we need to use a small set of numbers. And so the book does a really good example. And so what I want to imagine is we have some set of experiments we can run. And we are going to run these experiments. And so what we're going to talk about is something called a sampling distribution. And it's a probability distribution of samples. And so you take random samples of size n. Notice I'm going to little n here. We don't have a population, we have a sample. But we take these samples from a population. Now, generally we talk about the mean is the thing that we're looking at. And so the sampling statistic that we pull is usually the sampling distribution of the sample means. And what happens is I can run an experiment n times, and I'm going to get some random variable that I'm going to take its average. I run the experiment again n times, and I get some random variable in my sample, and I take its average. Each of these is a different experiment, a different set of data from the whole population. Sometimes my experiment grabs a result that overlaps. And I get a whole bunch of different samples I can take. And so the sampling distribution is the possible sample values, sample averages, that I can get out of my whole population. Now what we're hoping is that the average of the population should be equal to the average of my sampling averages. And what I mean by the sampling averages is I go back through and I grab all the samples I took and I figure out how many of them there were. I'm actually going to use a different variable than little case n here. So I go through and I count up all the different samples I took. So let's say I'll take, for right now we'll call them p. I go from 1 all the way up to p of them. I have so many of them coming through here. And that's going to be my average. Alright, I have, what I end up getting is x1 plus the average of x1 plus the average of x2 plus the average of x3, so on. And I've run p number of experiments. And as we do more and more of these, the population average and the average of all my experiments should be the same. And the standard deviation of all my experiments, or what we're going to call the standard error of the mean, is going to be related to the population standard deviation based on how many samples I take. What makes my sample? And this is really, really important because this ends up being how we actually do experiments. I'm being a physicist. There are an infinite amount of experiments I can do in my population. I can always, run the experiment again and again. And so when I draw from that infinite set of things, I'm only ever going to have a sampling average. But I can infer that my values are close to the true population, the truth for whatever experiment I'm doing. And so this two things link together. So what I want to do is I actually want to look at a sampling distribution and see what it looks like numerically. We want to be able to create one. And the book creates a nice one. It looks at people shopping, and it looks at how many times they went shopping in a month. And it just grabs 4 people. And so we have 1, 3, 5, and 7 as the entire population of these 4 people. And so I know for this entire population that the average is going to be the sum of all my values, so, which is 1 plus 3 plus 5, whoops, shouldn't be commas, plus 7, all divided by, I had 4 of them. So it's 4, 9, 16 divided by 4. Or I have an average of 4. 4 times, people go shopping 4 times in a given month. And the standard deviation, if I use that, the standard deviation is my x value minus the mean squared divided by the square root of, divided by n, all square rooted. Well, I have 1 minus 4, which is 3, negative 3 squared, so that's 9. 3 minus 4 is negative 1, 1, so that's 10. And I get 10 on the other side, so I'm going to end up with, 20 divided by 4, or 5. And so the square root of this is 5. Or you can plug this into your calculator, or you can come back. But we know the population's value, right? Because it's a small population. We can say, hey, this is of the population. But we're going to do an experiment where we select 2 of these at random, and 2 with replacement. So I can go back in and let's say I randomly grab 5. 5 goes back in the bucket, so there's a chance that I can grab the 5 again. Now, what I want to really emphasize is we're doing this on a population of 4. The math that comes out of this population of 4 will work with a population of 300 million. And so it might seem, why are we doing this for, something that we can easily find the population mean and the population standard deviation. The idea is the process here will work when we can't easily find it, and it's small enough we can see all the things that go into play. So if I were to look at the probability distribution of this as a discrete distribution, and my chances of getting a 1, 3, 5, or 7, with the fact that 6, 4, and 2 hang in the middle here, well, each of them is exactly 25%. There's a 1 in 4 chance for each one of these. That's my probability of my random variable. So what we want to do is we want to build this into what do all the samples look like. And so what we can do is we can create a sampling mean. And so what we can say is, what can happen? For my sample, right, for the first one, I can draw a 1 and a 1, right? I pull out a 1 and I throw it back in and I randomly grab a 1 again. Or I can grab a 1 and a 3, or a 1 and a 5, or a 1 and a 7. Those are my 2 samples, and those are all of the possible values I can get with replacement. Same thing happens if I draw a 3 first. These are the possible samples that I can get out. Well, if I take the average of my experiment, 1 plus 1 divided by 2 is 1. 1 plus 3 divided by 2 is 2. 1 plus 5 divided by 2 is 3. And so these are the possible experimental averages I can get. And so let me write all of them down. I'll write down all of my experimental averages and all my samples. Now notice I'll need 2 columns here, because I could also draw a 5 and a 1, a 5 and a 3, 5 and a 5, a 5 and a 7, a 7 and a 1, a 7 and a 3, a 7 and a 5, and a 7 and a 7. And let's see. And the averages that those particular experiments would get would be 3, 4, 5, 6, 4, 5, 6, 7. Now notice I can look at the frequency distribution of particular averages. And so notice 1 and 7 only get used once. 2 gets used twice, 3 gets used 3 times, and so I can build a frequency table of how often each experiment will give me a particular average. And so if I look at each experiment, my possible averages are, and the frequency of them, are 1 through 7. And there was only 1 1. There were 2 2s. There were 3 3s. There were 4 4s, 3 5s, 2 6s, and 1 7. All right, we come back here and look at the averages. I have 2 2s, 3 3s, 1 2 3 4 4s, 3 5s, 2 6s. So you see what I'm keeping a frequency track of? Of every possible set of experiments of 2, right? Now these were experiments of 2. I grabbed 2 things randomly from my population. And the averages of those, well, look at this. We can already start seeing that if I graph these, let's see, 1, 2, 3, 4, in a histogram, I'm getting a symmetric that's approaching a normal, minus my bad drawing. Right? We see a 1, 2, we have 1 in the first bin, 2 in the second, 3, 4, and so on. And so this is approaching a normal curve. And the probability for each of these is 1 in 16, 1 in 8, 3 in 16, 1 in 4, 1 in, or I'm sorry, 3 in 16, 1 in 8, and 1 in 16. All right, because we're looking at F over N, and we had 16 possible probabilities. And so this gives this a probability of, let's see, that's probability of X equaling 4 as being 0.25. And the probability of X equaling, this one is 1 in 16. The probability of X equals 7 is 1 in 16. And so we have a probability distribution that, even on the small curve, is symmetric. It approaches a normal. And so the idea is that if I have this small population of 4 things, as my population number and my N number increases, my distribution approaches a normal. Well, let's see what values we get out of this. And so what we want, if we look at this and we add up all the values we have here using our frequency distribution. So if I were to go in and say, use my weighted averages, come down here, the mean of all of these is equal to, right, the X value times its F over N, right? We did this back in the frequency distributions. And so I have 1 times 1/16 plus 2 times 1/8. And so when we add all of these up, we get 4, which is what our theory said, that those two should be the same. And, whoops, if I take the standard deviation of this distribution, X equals the standard normal divided by the square root of N, and we said that was square root of 5, and so this becomes the square root of 2.5, which equals 1.6. Well, let's see if we get these here. So what I'm going to do I'm going to come over, go to my TI-89, and I'm going to let it look at the stats. Now we can do this by hand, we can do this anyway. I'm going to let my technology do this for me. So first off, I'm going to make sure my lists are clear, which they are. And so my variables are 1, 2, 3, 4, 5, 6, 7. Right? Those were the possible distributions I had. And this was 1/16. This was 1/8. This was 3/16. This was 1/4. This was 3/16. This was 1/8. Whoops. Let me get back to my stats here. Edit. There we go. Sorry about that. Hit the wrong button on the keyboard. This was 1/8. And this was 1/16. And so I have my two lists here. I'm going back into stat. I'll do a calc. I'll do one var stat. My frequency list will be the frequency. And I have a mean of 4. And I have a standard deviation of 1.58, which was the 1.6 that we get when we calculated it out, knowing the population. So notice what we have here. We really have a system that can help us talk about an experiment relative to the population. Now that's going to be our linchpin here back and forth. We're going to learn it going forward. We're also going to need to reverse this. And so I will be able, from doing an experiment, to have a formula, this standard error of the mean, to link whatever the size of my experiment was and the standard deviation of my experiment to the population standard deviation. And I'll have a way of linking the average of my experiments to the average of the population. And that idea is called the central limit theorem. And in the central limit theorem, what really we're looking for is some things to link through. And I'll lay out the central limit theorem a little bit more in more detail. For right now, we're just going to say we've introduced this distribution of sample means, and we'll spell out the central limit theorem in the next video.